this sort of course. I would like to thank Sabine for organizing this interesting workshop and for inviting me to be here. And I also would like to thank Nick for exchanging his talk with mine, because I was not really in a condition to talk in London. That is better today. Okay, so this is the title of my talk. And what I'm going actually to discuss, the outline is the following. I would like at the beginning to give you a short motivation, a kind of connection with this topic of the conference here. Then I will discuss the elements of the non-commutative geometry spectral action, and I will give some phenomenological consequences of this approach, some successes, some problems, and some open questions in direction. And then I will present some work which we did the last couple of years, basically studying consequences of the non-commutative geometry spectral action. I will first study whether, is there any pointer actually? Okay.
Take out this.
Okay. So what I will first study is whether we can have any non-commutative corrections to Einstein's equation. Then I will study gravitational waves in non-commutative geometry, and we'll see how by using binary pulses we can put some constraint on one of the parameters of the model. And then I will investigate an odd kind of scenario where the Higgs field could play the role of the integral in this framework. Okay, so the motivation. Now, certainly we will agree that one profound question that occupies all of us is what is the nature of space-time. Certainly this question is intimately related to the issue of unification of all interactions with gravity, and as such is not independent of solving the problem of quantum gravity. Now, to my mind, the motivation for doing this approach is actually twofold. It can come from cosmology, it can come from particle physics. So what about cosmology? Well, as you know, we have a number of very successful early universe cosmological models, which nowadays can be tested with a variety of very precise astrophysical data. And in addition, the foundations of this model would be tested with high energy physics experiments, in particular LHC. Now, despite this kind of successful and golden era of modern cosmology, there is a number of open questions, namely the issue of the origin of dark energy and dark matter. Find the kind of successful but motivated from fundamental theory inflationary model, which are still seeking for a kind of answer. Now, the main approaches in cosmological models can be done using either string theory or other approaches to quantizing gravity, like loop quantum cosmology, spin cones, Wheeler-DeWitt equation, causal dynamical deviations, causal sets, and so on and so forth. So what I'm going to do here is instead use this kind of novel approach as far as cosmology is concerned, namely this non-commutative geometry spectral action. Now, as far as particle physics is concerned, the laws of physics at low energies can certainly be described by the sum of the Einstein-Hilbert and standard model actions. However, the first part, as you know, depends on the geometry of the manifold. The second one depends on the internal symmetries of your gauge group. So while the first part is governed by the homomorphism invariance, the second gauge symmetries are based on the local gauge invariance. And therefore, one might claim that actually the difficulties which we have in order to unify all interactions might be, the origin of that might be the difference between these two kinds of symmetry. In addition, there is a whole list of questions in particle physics. I gave some of them here, which still are likely for a definite answer. So what is the approach in non-commutative geometry? The approach here is the following. You might say that if you are much lower than the Planck scale, then you can safely consider gravity as a classical theory. But as you go closer to the Planck scale, then you cannot anymore forget about the quantum nature of your space-time, and this assumption is going to become an approximation, considering the Einstein-Hilbert kind of function. Now, the nature of space-time and therefore of the geometry, you expect that it's going to change as you approach the Planckian era in such a way so that at later energies you can get the picture of the diffeomorphism and internal DHC. Now, instead of doing a kind of extrapolation by almost 17 orders of magnitude, we're going to say how space-time should look at the Planck kind of regime. In this context, we're going to use a different kind, a sort of indirect approach, namely search for the freedom structure of the in the functional of gravity coupled to the standard model of particle physics at today's energy scale. So let me give you the elements of the non-commutative geometry spectral action approach. Now the basic idea here is that one could consider the standard model of electroweak strong interaction as a phenomenological model in such a way so that this phenomenological model is going to tell you how the geometry of space-time is going to look like so that at the end of the day you can recover the standard model. Which means that if you take this kind of approach, then the geometric space is going to be defined by this tensorial product of a continuum compact Riemannian manifold M times a discrete space F. So your geometry is going to be the product space of an internal geometry for your standard model and the continuous geometry for your space-time. This approach is based on three answers. The first one is exactly what I just told you, that we are going to consider this tensorial product space to be your space-time. And now this non-commutativity of this internal space set is going to be given by this spectral tripod, where A is an associative algebra. It actually plays the role of the algebra of coordinates. This will be the main input of this theory. 8 is the complex Hilbert space, and D is the self-adjoint operator in this Hilbert space, which plays the role of the inverse propagator Fermi. As I said, the main input in this approach is the choice of your algebra, and as such it was taking the product of the algebra of quaternions and the algebra of complex K by K matrices. K is an even number, and the first possible value that we can have, so that we can have the correct number of fermions in each of the two generations, it is equal to 4. If you take A to be equal to 2, then you cannot reduce to the 4. Now, so in this model, the fermions of the standard model are going to give you the Hilbert space.
I have a question. So the construct doesn't choose K from K,
no, the K cannot be equal to 2 because of the quarks. The first possible value is equal to 4, and then you can have 16 fermions in each of the three generations. Now, if tomorrow LHC finds many new particles, you can allow for the K to be bigger, to be an even number.
Okay, so it is constrained.
So it's, this model, it is, okay, you just pick it up so that you can give you the 16 fermions, that's all. But you could have it a higher number if you need. Okay. And the bosons of your standard model, including the Higgs boson, are going to be obtained in this spectrum through the inner fixations of the Dirac operator and your product geometry, which is almost a kind of continuous geometry, just the first approximation to a non-commutative space. Now, the third answer, which is the basis of this approach, is that the Dirac operator is going to connect the two pieces of your product geometry non-trivially. We're going to apply the so-called spectral action principle, which tells you that the action functional depends only on the spectrum. Spectrum here is what plays the role of the Fourier space for Fourier transform for continuous spaces of the Dirac operator, and it's going to be of this simple form where f is a test function and lambda fixes your energy scale will take it to be a reunification state. Now the three momenta of f which will come into the game are the f0, f2 and f4, which are obtained through that definition, and these three new real parameters are physically related to the coupling constant at unification, the gravitational constant, and the cosmological. So what now you are going to do, you are going to make an expansion of this in inverse order of the energy scale lambda. Now, actually for what I'm going to do here, I'm going to take only the bosonic part of this model. I'm going to do cosmology. If you want to do particle physics, you have to take the fermionic part as well. So then what you do, as I said, you are going to make an expansion in inverse orders of your energy scale lambda in terms of these coefficients A, which are the geometrical cylinder with coefficients. These are known for any second order elliptical differential equation. So what's the mean to do with this kind of definition here and the definition that I told you before for the three momenta of your test function, you can find capital F, you know A, so you can make this expansion. So if you go to do this expansion in inverse orders of lambda, then you are going to find the Lagrangian for the standard model minimally coupled to gravity in the Euclidean form. Certainly for me doing cosmology, I'm going to pass in the Lorentzian form, and I'm going to a signature, and I'm going to assume that through a weak rotation you can pass from the one to the other. This is something that mathematicians claim that is doable, but is not really good yet. So if you do that, that's how the action is going to look like. So what you can say is that you can, through this approach of the non-commutative geometry spectral action, obtain an elegant geometric interpretation of the standard model. So what are these terms here? We are going to have this Lagrangian, which we just created before. It contains the full standard model Lagrangian, Majorana-Mas terms for the right-handed neutrinos, gravitational and cosmological terms, where the gravitational terms include Einstein-Hilbert axiom with the cosmological term and topological term. In addition, you have conformal gravity term with the Weil-Caversham tensor, as well as conformal coupling of the Higgs to gravity. If you did not have these two terms, you are going to have the minimal capital standard model to gravity. So you need these two additional kind of. So this is important that you have these two additional terms. And something which is important.
So this thing would violate the universality of free fall.
Which one?
I mean, the fact that you have a couple of different particles in different ways, curvature, would you violate the equivalence principle?
Why?
I mean, not all matter is coupled in the
Yes.
same way.
No.
Then you
Yeah.
can expect things to fall at different rates.
Yeah.
Why not? But a different question. You have just one gauge coupling constant, so
No, I have three gauge constants.
you have three gauge
I have three
coupling.
gauge constants, which they don't meet at one point. So one of the things that I will say later, that one of the problems that you will have is that you do not have unification in the coupling constant.
Good.
I mean, you could have said to have unification, but then you have problems at the low energy. So if you want to fix the low energy physics with the standard model, then you have a problem. You do not have unification. But let me comment on that a bit later. So but you have three. You have G1, G2, G3. Okay? I will show that in a minute.
Is there anything peculiar about the expansion that determines the cosmological constant, or is it just a trivial thing? So you have this test function f, and you said you expand it.
Yes,
and you
it's
get
the
this
reverse
term.
orders. Lambda is not the cosmological constant.
I know
Lambda
that.
is not the
That's
cosmological
part
constant.
of
Okay,
the
it might cut
cosmological
off.
constant itself.
I have these three test functions f0, f2, and f4, which they come into the play. Okay? But lambda is not my cosmological constant. Probably it is a bad choice of notation.
No. I wasn't asking about your cutoff. I'm asking about, you said that the cosmological constant comes out.
No, I'm saying that three of the momenta of the f function will come into the game, and these three real parameters are related.
The
Gravitational constant to the unifications and to the topological constant. That's all.
Okay,
There's a
okay.
relation between f4 and lambda.
Okay.
Lambda not, okay, cosmological constant, not the lambda unity. That's all. It's not in inverse orders of the cosmological constant expansion.
Okay.
It's clear.
Yes. No.
Okay, and another thing which you have here is that the coefficients of the gravitational terms are going to depend on the particle physics model which you have Now, a remark here. The spectral action is taken at the unification scale, which means you can fix the boundary condition at the unification scale. I make this remark very explicitly because you can find in the literature, to my mind, incorrect answers where people assume this boundary condition to run with the energy scale, which is not the case, should not be done. Okay? So since your model lives naturally at unification scale, in other words, this lambda kind of cutoff that I gave you before, that means that this is a nice kind of framework in order to go and do some early universe model. If you want to go to lower energy, then you can do it through the normalization group equations. And if you want to do later time astrophysics, then you have to go and consider non-perturbative effects in spectral action. And this is an open question because, as I will show you a bit later, it's not really known how you can take into account the higher order corrections in this expansion. Okay?
So
No,
the action,
as a,
excuse me, the long action that you showed us contain dimension 5 operators and higher?
so now, as a matter of fact, I don't recall the name of somebody who proposed this kind of nice analogy which I did here. I'm sorry to get the name. Like that this kind of model can be similar to the Lincoln slot machine. In other words, you have some kind of entrances for your banknotes, and then once you decide what the banknotes will be, you have some other entrances for your coins, and if you give the right kind of ingredients, then you win. So by winning, you will get standard model. So in this approach, what you can say is that if you define at the beginning your banknote, which is this kind of algebra that I told you that is the main input, you give this fermionic Dirac operator, the representation of the algebra on the Hilbert space. All that is given by the spectral action. Then the coins, if you wish here, that you define your banknote, will be the spectral charges and the three moment of the test function that I just told you before, the 0, 3, and 4. And at the end of the day, then you win. In other words, you get the Young-Mills fixed model coupled to curve. Now, what is the phenomenology of that model? Now, the relation, I guess you asked or somebody asked, the relation between the Cage coupling constants coincides with this obtained grand unifying theories. Actually, this comes out once we go to do normalization of the kinetic terms. Now, the sine square theta w is the same value like what you get in SO10 and SO5. As you can see, I think we asked this question, we do not have the three Gauge coupling to meet at one point, okay, and therefore we do not specify unique unification energy. Now, you have...
Excuse me, let me just go back to that. But you're worried about the 5/3?
No, I don't worry. I'm saying that my three lines, they don't meet at one point. I don't worry. I'm saying what is the phenomenology coming out from that. I don't worry for the 5/3. I think the value that you get there is consistent with what you get in theories of learning.
No, I'm happy with that. But the point is that you have unification in the sense that there's a relationship between the three coupling constants.
Right, but I don't find a unique unification scale. That's what I'm saying.
But who cares?
They have to be fixed by...
I'm not saying that somebody cares. I'm
Who
telling
cares
you,
anyway?
I'm not saying that somebody, I didn't say that this is a negative or positive. I'm saying that this is the phenomenology coming out from that model. I'm just giving you a list of what has been found. I didn't yet say what was good, what was bad.
So you don't have to argue about whether the triangle is quote big or quote small and I think that's great. But the point is it is a genuine unification in that you have a relationship. The theory has only one parameter, and then that one parameter splits into the three parameters, the three gauge coupling between at a unification scale. So that's great.
Is that leading? Is that what's the RGE analysis? Is it leading order?
Yes, but this has not been done in that. Yes, it's a deleted order. Deleted order. With, I mean, a deleted order and some assumptions which we've done. For instance, in this kind of function, the non-linear of the Higgs to the reaching scalar will not take into account for this. So, again, here are the whole list of the phenomenological results. I have to speed up a bit of this theory. Now, let me go a bit further and tell you which are the problems. Well, if you take, as you asked, the one-loop RGE equations for the round of the gauge couplings and the Newton constant, you will find that they're not going to meet at one point. Now, the error is not very big, and you might expect that if you take higher order corrections in your round of the coupling, this might be true. Now, the mass of the Higgs was actually out from the more recent data. It was found to be 170 GeV. Of course, the value is going to depend on what is the value of the gauge coupling simplification, and therefore you might expect as well this to be changed. No new particles, but remember I said we took the smallest allowed value of this even number k, and that if you take the higher value, this might as well give you more particles in case they are found with an EG. No explanation of the number of generations. This was a kind of physical input put in this approach. No constraints on the values of the couplings. Now, the speculations which can be proposed on the spectrum of the non-commutative space on quantum gravity is that this small deviation which will be found between the results and between the predictions of the theory and the results might have its origin in the fact that we took this kind of a simplified approach to a non-commutative geometry, and it might be that as you go to much higher energy, then you have to take a less trivial, more commutative space, whose limit is going to be then 4 plus f, and if you can go a bit even further, a bit more wild kind of extrapolation or speculation, you can say that as you go above the Planck mass, then Planck energy, then we cannot talk about geometry altogether. So the quality is
Sorry to interrupt. Can you explain maybe how you get 170 GeV for the Higgs mass?
Sorry?
How do you get 170 GeV for the Higgs mass?
That's what it comes out of the model at the end.
Is that a renormalization?
It's a normalization group to one group.
So you can probably modify that with higher dimensional operators.
Certainly, but I'm saying all the RGE that was done in that model was done up to one loop, and it was done as well neglecting the coupling of the Higgs field to the Ricci curve. That's what was done, and this result was found. Now somebody has to redo it, and people start redoing it. But the most complete analysis was done under that framework, and certainly. Now the next steps to my mind that have to be taken exactly is to consider higher order corrections to the spectral action, which might cure these problems. And the second and actually there is a kind of very recent work by Chancelin and Kohns when they consider what will happen if you take higher order corrections, however for a space which is by no means physical. So they took that your 4-dimensional space is going to be the product of a 3-sphere of a radius A, that's going to give you the space, and of a circle of radius beta, which is the inverse of the imaginary time. And some approaches are under the way in order to be able to generalize that to a more realistic space. And the second thing that has to be done is to take a less trivial non-commutative space. There is absolutely no approach to that whatsoever. So let me now go and tell you what we did considering cosmological consequences of this approach. So the first is to study corrections to Einstein's equations. Okay, so we start from that action, we throw whatever you want to give.
Yeah, sorry to hold you back, but before the cosmology, where is the arbitrariness in the Kawa couplings? Because you just had 3 moments of your
yes, this cannot be said. One of them I'm going to fix it later on through the gravitational waves. So I found pretty interesting results that I can fix it through astrophysics, but they have not been a priori fixed in the model.
But yeah, so why are the Kawa couplings not fixed if the model has this 3? Are they not in the model, or?
They were not fixed. They could not be fixed.
But,
I don't understand
if
also why.
If you say you have 3 parameters which become the gauge coupling constant,
I can get this F0, F2, and F4.
Right.
These, they can be physically related to whatever I said, but these they were not fixed. They were 3 parameters of the model.
How many parameters did you start with? How many free parameters did your model start with?
Depends on which terms you want to care for. If you care for the gravitational part and the Higgs part for which I have 3, 0, 2, and 4.
Including all the rest of the
It will be much more. I don't know, I
there
cannot
may
be
more.
that. So it will be much more, certainly. It will be much more. And I don't care for the fermionic part because I was not doing particle physics, I was doing cosmology. So now, how many are the positive parameters? I don't know. I can look it up and try to give you an answer, but I cannot give you the number now. I don't know how many parameters. Okay, so if you take, in other words, the part that has the gravitational part and the non-minimal coupling between the rich scalar R and your scale Higgs field phi, which I did not here by yet. So this is your action. With the action, you can find the equations of motion. So if, for instance, you start at the beginning, yes, sir. If you neglect the non-minimal coupling between the geometry and the Higgs field, then you will find that certainly the barrel tensor in such a background is going to vanish, and therefore you do not have any change from your Einstein's equation.
Can you go back to the previous slide?
No, I would like to go a bit ahead because I've never finished if I have 10 minutes. Okay.
So no, I was just wondering the kinetic term of the Higgs field. I just missing.
What are you missing?
The kinetic term of the Higgs field. I'm not seeing the.
Here I have this is my Higgs field. Okay,
Yes.
with gravity. I have not put any potential in that for that.
But where is the kinetic term of the Higgs field? You're also considering the kinetic term of the Higgs field.
Which time?
It's missing, of course, yeah.
Yeah, but you're also
Sure.
considering the
Yes,
kinetic term
yes,
of the
yes.
Higgs field.
But I don't for that. But I wanted to know if I don't care. Okay, I want to start with the Einstein's equation. So this is what I'm going to change.
But you're considering the dynamics of the Higgs field as well in what you're going to do.
No, as I said right now, starting from here, I neglect the Higgs field.
Ah,
Okay? So if I neglect the Higgs field, I have now, let me go, I will go to that in a minute. Okay? If I neglect the Higgs, that's what I get, which means if I neglect this coupling, that means I do not find any change in Einstein's equations. Okay? However, as you go to higher energies, you cannot neglect that anymore, so you have to take that into consideration. If you take that into consideration, that means you are going, sorry, before saying what will happen if you have the Higgs field, sorry. If I neglect the coupling between the Higgs field and the background, okay, then for Friedman electrons and what kind of universe, I have absolutely no change. So I have to take anisotropic spaces. If I take anisotropic spaces, so I take a Bianchi-fied mode, if you take this geometry and you take the action I gave you before, forgetting about the Higgs field, and you go to see how the equation of motion would change, we found out that this is your new equation of motion. You are going to have some terms which depend on the 4 products of the time derivative of a slowly varying action for cosmology, which can be neglected. You have another correction which comes at equal footing as Einstein terms. However, it depends on n squared, which means that if you have homogeneous background, it's not going to work, and therefore you can conclude from that that if you neglect the coupling of the Higgs field with your background, then you are going to have that the equations and Einstein's equations are going to change only if you take inhomogeneous anisotropic background. However, as I said, if you go to higher energies, you have to consider the Higgs field background. If you consider that, and now you are going to write how the equation of motion will be, that's how your equation of motion will look like. In other words, the effect of a non-zero Higgs field is going to create an effective gravitational constant. Okay? An equivalent way that you can see this effect is if you consider the effect on an equation of motion for the Higgs field, some constant gravitational field, then that's how your Lagrangian will look like, which means that what you are going to get is that the self-interaction of your Higgs field is going to be increased, what you see here.
Normally, non-minimal coupling to a scalar field produces also terms in the energy momentum tensor that go like the second derivatives and are not positive definite.
But this might be very small corrections, I think. I think that this is...
No, look here, it's okay, because this term can only be generated in the logic of effective field theory via quantum corrections. So you know this term has to be there for normalization reasons, and it all depends on the coefficient with which this term enters.
No, I mean, just the action she wrote.
Yeah,
The action she wrote has the second derivative of the Higgs field, and that's not positive definite.
It
And
has,
we have
where
unbounded.
does it have the second derivative?
Yeah, when you vary that action.
No,
there
but
are-
this is standard. Look, this is
Yeah,
standard.
it's very
It's a
standard.
standard.
It's very standard, of course.
This is
Just
And
the
you get
effect
second,
of including
and you get second
the,
derivatives coming from the.
the 1/12, exactly which is one.
No, there is something more. But okay.
Let's discuss it.
Sure.
Yeah? Okay, so now let's start with this other thing which can fix the, if you have the gravitational waves in this context, it can fix this three parameter that I said before, the zero, one of the three moments of the test function. So what is the idea here? Okay, here is your equation of motion. Now, for what I'm going to do, I'm going again to neglect the non-minimal coupling between the geometry and the background. So what I would like to do is I would like to find some way in order to be able to put a constraint on this parameter, which is nothing else than f0, one of the three moments, okay? So which I can reparameterize, so f naught or a naught or b square, if you wish, is the same thing for the same thing here. And the only constraint we were aware of for curvature square terms that was given for terms of a different form but of the same order was done long ago in 1970 by Stern, taking into account orbital precession of Mercury, something which clearly cannot be used here because, as I told you, we cannot, in the concept of homogeneous and isotropic backgrounds, find any restrictions here, cosmology or solar system test, just because we do not find any difference from the standard GR kind of approach. So we would like to use binary pulses in order to be able to put a constraint on this F01 on my three parameters. So what we're going to use, we're going to start with energy loss to gravitational radiation by orbiting circular binaries. So this is the standard approach that we can take. So of course it is given in terms of the time derivative of the first order general solution for the perturbation against the Minkowski background, which is given in terms of multiple moments. So if you go to do that, you will find that you have a resonance at a particular frequency, and this one particular frequency is going to give you the limit at which you expect to have important changes from general relativity. And actually this particular frequency means nothing else than the relation that you have in this theory with this fundamental scale at which you cannot neglect non-commutative effects. So if we take, for instance, our circular binaries that I will give you in a moment, the constraint that we are going to put is that their orbital frequency omega has to be smaller than this critical frequency, otherwise we are not going to recover at the limit of beta goes to infinity or A naught goes to zero, the general relativity standard kind of result. So if I get this kind of binaries there, I'm going to constrain my beta so that I'm not away from the accuracy of the GR result. So if you do that, you will find out that the strictest constraint which you can put on this beta, or in other words on this F naught, it is given from this value here, which certainly is not a very strong limit, but a priori it can be improved because this correction it is inversely proportional to the frequency of the orbital frequency omega. So if we expect to have data from more binaries which are nearby there and which they are rapidly rotating, then we expect this one to improve by some order of magnitude. And now the last thing I would like very briefly to comment is this possibility that inflation could be driven by the Higgs field. So this is an old idea that has been proposed by many people and has been worked by a number of people. And this has been failed. For instance, the main obstacle that we face once you would like to accommodate the CMB results, then you will find that the Higgs mass should be about 10 orders of magnitude bigger than what particle physics tells you. So, let me start again. This is my reaction. This is now find my Higgs field. The potential is the standard lambda phi to the fourth minus m square phi square. These are the values that the boundary conditions that you have at your lambda scale, okay? So, okay. So what we're going to do, so here is the problem I told you before that some people did, and to my mind is wrong. It's difficult to do astrophysics because we don't know the rank of these A, B, C, Yukawa and Majorana parameters. So what some people have done as an answer is to consider these relations as a function of energy, which to my mind is incorrect. So that's the difficult thing in being able to do some kind of more astrophysics to that moment. So what we're going to consider is, first of all, we start with the minimally coupled model, so psi equal to 0, and we would like to see if we can, through two-loop quantum correction, get a flat potential. So, so this is the classical potential that we're going to have, okay? And we're going to calculate the normalized values of the parameters lambda and mu. So at high enough energies, you can neglect the mass term. So this is your potential. So as you can see from this plot here, for any value you consider of your top quark mass, you can find the value for the Higgs mass, so that your potential, you can see it, just about to develop a second metastable union where your potential locally it is flat. For instance, for the values I gave here, the first black curve is the place that it becomes a bit flat. Now, what is the difficulty that you have in these approaches? Here I give the first and second slow roll parameter, epsilon mu. So in order for this model to be successful, you need a sufficient number of free-falls. Because it's a number of efforts where epsilon and mu has to be small for considerable time. And the price that you pay in doing that is that your potential becomes large. In other words, it's difficult to go and fit the double map kind of design that you have here. So this is the problem that we have. Anyway, the approach that then we followed is the following. We calculate the renormalization of the Higgs self-coupling with a minimal coupled standard model. Then we construct an effective potential, okay? Effective potential which fits this renormalization improved potential where we found it to be locally flat. And then we're going to find which kind of modifications are going to have to be considered if we take that we have conformal coupling. C is not 0 but 1 over 12 for our notation. So for instance, here I give you again this plot. So this is the place where it becomes flat. So this is the analytic fit to the Higgs potential that we're going to have, okay? And this is given in terms of the top quark mass. So, if you go to study what will be the modifications if you take conformal coupling, which is important not only in this context, but for any theory that you have conformal coupling between the Higgs and the background geometry, then what you will find is that in that case, I have to go a bit faster so I'm not going to say that, what is going to find is that in order for inflation to be realized, then the top quark mass is going to fix the Higgs mass with very high accuracy. Now if I want to show that, here see this plot. So in this plot, the blue color corresponds to conformal coupling, the black color corresponds to minimal coupling, this line, the continuous line, gives the potential, and this dotted line, it gives the maximum value of the epsilon, the first low roll parameter at horizon crossing. So what you can find is that you see the price that you pay, as I said before, because you consider small enough epsilon, is that the value you get for this quantity, which is what you are going to compare with the WMAP7, is much higher than what WMAP7 does. So what you get out of that is that if you include the running of the self-coupling at two loops, then you can find successful if-falls. In other words, you can find enough inflation. However, the CMB data make the predictions incompatible with the value of the top quark. You might consider that this might be improved if instead of doing this study in the case of a Minkowski background, you tend to do it in a de Sitter background. Or if you go to consider what will be, if for instance we take the rank of the gravitational constant, you will find out that you can improve upon these results, but still you cannot make it. Now let me make a very small comment. What about large values of xi? Because remember, here I'm talking about xi 1 over 12. And there are many people, notably supposed collaborators, who advertise the xi 10 to the 4th. Okay, so these models, I believe, are as well ruled out for the following reason. You have to study the conditions for the generalization of the lower inflation in the Sitter space, where therefore when you take this quantum gravity correction, the Coleman boundary potential that we all use, there is going to be, this is the limit, this is Minkowski balance. This has been done long ago by, I cannot pronounce his name, Julacic and Prokopiev. So they have done this analysis, and for one loop, no minimally coupled scale lambda 5 to the 4th theory, and this is the constraint which they found for large negative values of xi, so they have to be ruled out. Actually, to keep commenting on that, conventional cosmological models with psi 10 to the 4th have as well been criticized by this group of people, Burgess, Lee, Trotter, and Barbon and Espinosa, because what they say is that actually the validity of your theory breaks down and at a scale which is lower than the scale that you should know your theory. So in other words, if xi is about 10 to the 4th, then the theory ceases to be valued at this scale, and you need to know it at that scale. Of course, for exceed the order 1 of the 12, it's not easy. And more recently, namely yesterday, I found out of another interesting criticism of this approach by Xavier and a student of his, that they said that actually models with large non-minimal coupling are going to be ruled out because of unitarity violation, and they have some arguments which I'm afraid we discussed yesterday. I didn't have a lot of time to see that, but this is the word. So these models have been measured. So since I ran extremely late, let me finish with my conclusion. So I found this very beautiful picture. So I thought, yeah, downtown, I think I love this, no? So what? Excuse me?
Oh, sorry.
Okay, so what is actually this non-commutative geometry spectral action is going to extend our usual notion of commutative spaces by considering the spectral tripole on a space which is composed by the four-dimensional compact Riemannian manifold and a small non-commutative space. Now, it offers a simple, kind, elegant Lewis explanation for the standard model, and it offers a reasonably good framework in order to do early universe cosmology. Certainly much more work has to be done in the foundation of this approach, and certainly much more work can be done in the phenomenology. Thank you very much.
Yeah, sorry, I have a short question. So what fixed the value of psi, the nominal coupling between the Higgs and
To be one of the 12.
Yeah.
Apparently, this comes out to be this conformal coupling, and what they say is the fact that they go through the Dirac operators generically gives xi equal to 1 over 12. Other approaches of no commutative geometry do not give it that. And for me it was important as a question, but I don't have the answer, and neither Cons or Chamsedy have an answer on that. How come? And the part, a sector of your action has conformal coupling, and the other section no. I mean, is there any kind of intrinsic reasons for that? I don't have the answer. They don't have the answer. I cannot tell. But the fact that you take this Dirac operator, which always apparently gives you here conformal coupling. And there's an open question as well if this is generic or if you could. Actually, if you take x equal 1 over 12, you probably know, and you take the beta function for psi, then it always is going to be stuck at 1 over 12. You cannot run it, because there is a factor somewhere that comes something minus, psi minus 1 over 12. So if you fix it at 1 at scale, then it becomes at that equal. It becomes so you cannot run it, but that's what
I think this may not be a fundamental problem, but I think it's potentially a very serious problem when confronted with phenomenology, because, as you know, universality of free fall has been tested with incredible accuracy. It's probably going to be one of the most accurate tested principles very soon. And any even virtual contribution to the mass of an object, which would differ for different substances when they have different amount of their mass coming from, let's say, the the electroweak sector would make matter fall at different rates. I don't think, and if you have fixed this non-universal coupling at some value, then I think you're going to have a hard time escaping the bounds.
Look, I don't know. I haven't thought. I have to think about that. I don't know if this is the problem. Yes.
So at some point we actually had this very interesting coupling 1/1 minus the Higgs to the energy momentum tensor. What sector is that universally the case, or is it the high energy limit, the low energy limit?
All of that is the high energy limit.
Is that the high
All
energy
of that
limit?
is the high energy limit.
Okay, so
In that aspect, it resembles a bit like chameleon models.
yes, and also the degravitation models
Exactly.
are valuable.
Yeah,
But in what sense? So in what sense is it high energy limit? Because it looked like you integrated out the Higgs, so you stay
No,
below.
high energy limit, because what I'm saying is that all of that is the when you make the expansion of the interaction, you just pick the higher order in that sense.
Oh, okay. Yeah, but you surely have to stay below the Higgs mass.
Certainly,
It's Chi-Newton renormalization. That's where it comes in, right?
So, two conceptual questions. Why are you motivated from the non-commutative geometry to the hypothesis that the
Why movement?
why are the two topics together? That is, why do you go from the non-commutative geometry? You discussed the non-commutative geometry unification. You also discussed the hypothesis that the inflaton is the Higgs.
The hypothesis, excuse me?
That the inflaton is the Higgs, which is also a very interesting idea. But there's something tie the two ideas together.
Well, I mean, my starting point was this non-commutative geometry spectral action. This is the model that has been advertised by a lab collaborators. They did the phenomenology of the standard model. Since this model is fixed at the unification scale, we said this is a reasonable kind of framework in order to do early universe cosmology. So let us see, I mean, the result of the Higgs field can be applied to any model, as I said, that is conformal coupling between your Ricci scalar and in this context, you see, they start people and they say, I have this coupling, non-minimal coupling between the Higgs field and the background. And I'm saying, here I have a theory that motivates this non-minimal coupling and fixes it at conformal coupling. So this is the framework that sounds reasonable to study the Higgs field as neighborhood. But the results, as I said, are applicable to any model coming from anywhere. An example is this one, that can help you that ratio, that the model had sine per 1 over 12 are h2. What's it?
Well, then I'm missing is the basic statement that in the non-commutative geometry unification, there is no freedom to add an inflaton. So if there is an inflaton, it has to be.
There are other scalar fields in the field.
Okay.
And we have started one other scalar field and it had not worked. And there is some other scalar fields as well that we have not studied. And said the first thing we have this field, why not to be different? Then I have to consider other scalar fields which naturally exist in it. For instance, this lambda has been advocated that could be promoted to a field. And therefore we could see if this would play the role of the inflaton. I don't know, because the theory does not give me a potential. If I have a field that does not have a potential, it's difficult to see how it could play the role of the inflaton. That was a simple thing. I mean, to consider if this field could be the inflaton, that's all.
But can I elaborate on sorry, just on these, no, I don't want to take away another question, but just on these, because I think that's a very important point, right? Why would you want to accommodate inflation in that model? Since you have dimension 5 operators anyhow, you know this cannot be a fundamental theory. It's normally normalizable.
Excuse me, in all the models that people try to put inflation, we find something very fundamental. People try to see if inflation, could be accommodated to any model. One case is that.
Well, you want to trust what space-time is,
but
right?
Here I also
you
said
don't
that
know whether you...
this is, as I said, it might be that I don't need inflation.
Precisely.
But I don't know, because as I said before, one of the points that my mind have to be done is to see the parent theory from which this one can come. But this, nobody knows it. I certainly don't know it. And So I work with this effect. So certainly it might not be needed, but can you imagine that I go now out and I say in this context we neither need deflation? I mean, everybody's going to.
Yeah, but it would be nice fight.
I cannot say that we don't need it. You have to prove it. I don't know the parent theory to say we don't need it.
No, but this is it's good to be vulnerable and not bad. If you can't make inflation work in non-commutative geometry, that's good for non-commutative geometry, because it means that you're pushed into a little corner where there has to be another explanation for the horizon problem, and that's good because there are other explanations on the table.
It might be. It might be, as we said, that I don't need deflation, but I cannot prove you that I don't need it.
That's important.
I cannot prove it right now that I don't need it. I cannot prove that any of the other scalar fields cannot be the inflator right now that we talk. I can tell you that this one cannot be the inflator.
Very common. You should be careful calling it generally speaking non-commutative geometry, because there are different approaches. Some of them where you have much more freedom between edges.
Here you don't have that much freedom in this approach.
In particle physics, we're buried in freedom. It's good to have models which have no freedom.
Here I don't have that much freedom.
That's good.
If they are generic, then it's good to have.
No, it's good to have models. It's good to have models that don't work or almost don't work. I mean, this gives us some hope that there could be a model which actually explains something.
So let's deflate the coffee break and a short question.